every atom in your body, every star blazing in the night, every galaxy tearing through the void, they all scream one impossible truth: you shouldn't be here. The universe, in its earliest, most violent moments, played a game with the highest stakes. It birthed matter, and with it, its merciless twin, antimatter. According to the cold, hard rules of physics, for every particle that makes you an exact opposite, a mirror image should have burst into existence. Then, in less than a breath, matter and antimatter should have met, colliding in a cataclysmic flash, annihilating each other into pure light. The cosmos should be a vast, empty graveyard of photons, a perfect, silent void where nothing could ever form. But look around. You're here. Galaxies rage, stars burn, life blossoms. Our very existence is a cosmic defiance, a mind-bending anomaly that rips apart the universe's most fundamental symmetry. How did we escape total annihilation? Our universe, this sprawling tapestry of stars and nebulae, is built on a cosmic lie. The architects of creation, the fundamental laws of physics themselves, demand absolute balance. They are the universe's most meticulous accountant, meticulously tracking every particle, every quantum fluctuation, and their ledger screams, for every debit, there must be a credit. For every speck of matter, an equal opposite speck of antimatter must be born. This isn't some abstract theory. It's a direct consequence of the Big Bang itself. When our cosmos exploded into being, a furious, superheated soup of energy, it immediately began to cool. As it cooled, that pure energy crystallized into particles. But here's the cosmic catch. For every electron that burst forth, an anti-electron, a positron, also appeared. For every proton, an antiproton, a perfect, symmetrical birth. Now imagine what happens when these cosmic twins meet. It's not a gentle handshake. It's a furious, absolute obliteration. A particle and its antiparticle are like two perfectly balanced, hypercharged magnets that, when slammed together, don't just cancel out. They incinerate each other. They vanish in a blinding flash, unleashing all their mass as pure, unadulterated energy. Think of it like a cosmic debt. You swipe your universal credit card, creating a matter particle. The universe's accountant immediately debits your account, creating an antimatter particle. The ledger must always balance. In the blistering, infant universe, this annihilation was instant, brutal, and relentless. As matter and antimatter screamed into existence, they immediately sought each other out, locking into a dance of mutual destruction. The early cosmos was a chaotic, unimaginably hot forge, where creation and annihilation raged in perfect harmony. Every fraction of a second, particles and antiparticles were born, then immediately collided, returning to the primordial energy bath. The laws of physics dictated this perfectly balanced, zero-sum game. So, if the Big Bang truly played by its own rules, if its cosmic scales were perfectly level, then every proton, every electron, every neutron that ever formed should have been instantly erased by its antimatter twin. The universe, after that initial fiery burst, should have settled into an eternal, featureless expanse of pure light, photons streaming endlessly through the void. No atoms, no stars, no galaxies, no you. But the universe didn't balance its books. It cheated, or more accurately, something tilted the scales. We stand on a cosmic anomaly, a violation of the universe's most fundamental symmetry. We are the survivors of an impossible cosmic war, the tiny, inexplicable excess that somehow endured the universal purge. This is the universe's greatest paradox, the crushing weight of everything we see against the absolute certainty of physics that nothing should exist. What cosmic force dared to break the perfect symmetry of creation? What allowed matter to win the greatest fight in history? And where did all the antimatter go? The universe, it turns out, is a master of hiding its secrets in plain sight. For decades, this cosmic vanishing act, the missing antimatter, haunted physicists. They knew the rules. They saw the impossible outcome. And then, a brilliant mind, the Soviet physicist Andrei Sakharov, crashed into the problem in 1967. He didn't just ask what happened, he asked what would need to happen for matter to survive, he laid down 3 brutal, non-negotiable conditions, like a cosmic detective outlining the steps a killer must have taken. These are the Sakharov conditions, and they are the universe's secret recipe for baryogenesis, the birth of more matter than antimatter. First, baryon number violation. This is the big one. Baryons are particles like protons and neutrons, the stuff that makes up atomic nuclei, and thus everything solid around you. Their baryon number is like a cosmic ID card. Protons have a baryon number of always 1, antiprotons 1. In a perfectly symmetrical universe, the total baryon number must always stay the same. You can't just make a proton appear without also making an antiproton or an electron. But Sakharov said, nope. To get an excess of matter, the universe must, at some point, have been able to rip up those ID cards. It had to allow processes where the total number of baryons changes, where you can create a proton without its antiproton twin, or destroy an antiproton without destroying a proton. Imagine a cosmic bank where suddenly you can withdraw money without making a deposit, or erase debt without paying it back. This is the ultimate cosmic cheat code. Second, C and CP violation. This gets weird. Even for cosmic standards, C stands for charge conjugation. It means if you swap every particle for its antiparticle, the laws of physics should remain identical. CP stands for charge parity. It means if you swap particles for antiparticles and mirror the entire system, like looking at it in a mirror, the laws should still be the same. Think of it like a cosmic dance. If you swap all the dancers for their anti-dancers and then look at the whole thing in a mirror, the dance steps should still be identical. But Sakharov said, no, the universe's dance floor must have a subtle, almost imperceptible tilt. It needs to have a slight preference, a tiny bias, for matter over antimatter when these transformations happen. If the universe truly treated matter and antimatter identically, then even if baryon number was violated, any excess created would simply be wiped out again. There needs to be an inherent fundamental asymmetry in how they interact, a slight favoritism towards matter. It's like a rigged coin flip, but the rigging is so subtle, so tiny, that it took physicists decades to even detect it in our own particle accelerators. Third, out of equilibrium processes. This condition is about speed. The early universe was a cosmic pressure cooker, Nolga hot and dense. If the universe stayed in perfect thermal equilibrium, a state where creation and annihilation balance each other out, then any matter excess created by the first 2 conditions would be immediately erased. It's like trying to fill a bucket with a hole in the bottom. No matter how much water you pour in, if the hole is big enough, the bucket never fills. To keep the matter from being wiped out, the universe had to expand and cool faster than matter and antimatter could find each other and annihilate. It needed to literally outrun the destruction. This created a sudden, rapid freeze-out, a moment where the universe cooled so fast that the tiny, Sakharov-approved matter excess was locked in before it could be destroyed. It's like flash freezing food to preserve it. The universe flash froze its tiny matter asymmetry. Now the standard model of particle physics, our most successful theory of how particles and forces work, does contain hints of these conditions. It shows tiny, almost imperceptible violations of CP symmetry in certain particle decays. It even suggests that baryon numbers can be violated, but only at incredibly high energies, far beyond anything we can reach in our most powerful colliders. The problem? The violations we know about in the standard model are far, far too weak. They are like a whisper when you need a scream. They can only account for a matter-antimatter asymmetry so small that the universe should still be empty. They predict a cosmos with perhaps 1 proton for every 10 billion Tamer photons. We need 1 proton for every 1 billion Anar photons. That tiny difference is the entire universe you see around you. The standard model, as it stands, falls short. It can't explain why we're here. It's like having all the ingredients for a cake, but not enough flour to make it rise. This means something else. Something beyond our current understanding must have happened in the universe's first fleeting moments. Something that violently tipped the scales, ensuring matter's triumph and our improbable existence. The universe had a secret weapon, a hidden mechanism that allowed it to break its own rules. And finding that mechanism is one of the greatest quests in modern physics. If you're finding this cosmic mystery as mind-bending as I am, smash that like button and subscribe. We've got so many more secrets to unravel together. The Standard Model, our bedrock understanding of cosmic mechanics, whispers of matter, but it can't scream our existence. The tiny asymmetries it offers are a mere tremor when we need an earthquake. This profound silence from our best theory has driven cosmologists to the edge of the theoretical abyss, forcing them to imagine radical, almost desperate solutions. They are searching for the hidden cosmic engine that violently tipped the scales. One leading contender involves the most elusive, ghostly particles in the universe, neutrinos. We know these subatomic wraiths zip through everything, rarely interacting. But what if the early universe harbored super heavy neutrinos? Imagine them not as the wispy specters we detect today, but as cosmic titans, primordial giants that vanished almost as quickly as they appeared. This is the heart of leptogenesis. The theory proposes that these monstrous neutrinos, born in the universe's first scorching moments, were unstable. They decayed, but critically, they decayed asymmetrically. Instead of splitting perfectly into equal parts matter and antimatter, they had a subtle, fundamental bias. They preferred to create slightly more leptons, like electrons and their cousins, than antileptons. Think of it like a cosmic coin that, when flipped a trillion times, lands heads just a tiny fraction more often. This tiny persistent bias, amplified by the sheer unimaginable numbers of these decaying heavy neutrinos, created a surplus of matter. That initial lepton excess then, through other exotic processes, converted into the baryon excess, the protons and neutrons that built our universe. These ghostly titans, long gone from our cosmos, might be the true architects of our existence, their brief biased decays sowing the seeds of all matter. But what if the answer isn't a new particle, but a violent cosmic upheaval? Enter electroweak baryogenesis. Picture the early universe, just a fraction of a second old, as a boiling pot, not of water, but of fundamental forces themselves. The universe was incredibly hot and dense, its forces unified, acting as one. But as it expanded and cooled, it went through a dramatic Fort-E phase transition. Like water suddenly freezing into ice or boiling into steam, the fundamental forces separated. This wasn't a gentle shift. It was a furious, ripping event. Bubbles of a new, distinct vacuum, regions where the forces had settled into their modern, separate forms, began to nucleate and expand. At the edges of these expanding bubbles, a cosmic tempest raged. The conditions there were utterly unique, a violent, out-of-equilibrium environment where all three Sakharov conditions could be met simultaneously. The universe's C and CP symmetries were brutally violated at these bubble walls. Matter and antimatter interacted differently, their dance steps fundamentally skewed, and crucially, baryon number was violated. Imagine these bubble walls as cosmic blenders churning the primordial soup. As matter and antimatter particles slammed into these turbulent boundaries, the antimatter was preferentially destroyed or pushed away, while matter particles were created or allowed to slip through into the newly forming vacuum. This violent, non-equilibrium process literally swept a tiny excess of matter into our universe, locking it in before it could be annihilated. The universe didn't just cool, it underwent a cataclysmic, symmetry-breaking rupture that forged the very stuff of reality. And then there's the truly mind-bending possibility. What if the antimatter isn't gone at all? What if it simply exists elsewhere? This theory suggests that the universe didn't just to produce one cosmos. Perhaps the Big Bang was so immense, so fundamentally chaotic, that it violently ripped space-time itself into two distinct realms: our universe, dominated by matter, and a mirror anti-universe where antimatter reigns supreme. Imagine two cosmic twins, born from the same primordial explosion, but each carrying the opposite charge. In this scenario, the total amount of matter and antimatter across both universes would still be perfectly balanced. We simply happen to live in the universe where matter won the local lottery. Our missing antimatter isn't missing, it's just in the cosmic house next door, forming anti-stars, anti-galaxies, perhaps even anti-life. We might be just one side of a cosmic coin, forever separated from our antiparticle doppelganger by an unimaginable fundamental divide. These theories are not just abstract mathematical constructs. They are desperate gambles, bold attempts to tear back the veil and expose the universe's deepest secret, why anything exists at all. They push the boundaries of what we know, forcing us to consider entirely new particles, cataclysmic cosmic events, or even parallel realities. The very foundation of our existence hinges on uncovering which of these radical solutions, or perhaps something even stranger, allowed matter to triumph over annihilation. The theoretical landscape is rich with possibilities, but the ultimate truth demands proof. Scientists aren't just speculating, they are relentlessly hunting for the universe's cosmic secret, smashing particles and scanning the heavens for any whisper of the missing antimatter's fate. This isn't just an academic exercise, it's a relentless, high-stakes detective story where the very fabric of reality is the crime scene. Our most direct assault on this mystery happens in colossal underground cathedrals of science, particle accelerators. Here, engineers and physicists recreate the conditions of the early universe, albeit on a microscopic scale. They accelerate particles, often protons, to nearly the speed of light, then smash them head-on, releasing bursts of pure energy. From this primordial fire, new particles are born, mirroring the processes of the Big Bang. The goal? To witness the universe's cheat sheet in action. We are meticulously searching for any tiny, undeniable sign, Baryon number violation, or a stronger than expected C or CP violation in the decay of exotic particles. If the universe harbored super heavy neutrinos, for instance, smashing particles might reveal their ghostly signatures or provide clues to their properties. Every collision is a desperate attempt to catch the universe in the act, to see that fundamental asymmetry unfold before our eyes. The data streams are immense, the experiments unbelievably precise, pushing the very limits of human ingenuity. We're trying to find the cosmic thumb on the scale in the aftermath of a trillion miniature Big Bangs, but the hunt isn't confined to Earth. The cosmos itself holds ancient, chilling clues. If the universe truly spawned entire anti-galaxies, then we should be able to detect them. Imagine a galaxy made entirely of antimatter, anti-stars, anti-planets, perhaps even anti-life. While we can't directly see antimatter, it looks just like matter, we can see its signature of destruction. If an anti-galaxy ever collided with a matter-dominated galaxy, or if a rogue anti-star ever drifted into a cloud of ordinary gas, the resulting annihilation would unleash a burst of gamma rays so powerful, so distinct, that our telescopes should spot it from across billions of light years. It would be an unmistakable cosmic explosion, a beacon screaming the existence of antimatter. Astronomers have spent decades scanning the heavens for these annihilations. They've searched for gamma ray hotspots, for unusual energy signatures that betray the clash of cosmic opposites. And the results? Deafening silence. We see no compelling evidence of large-scale antimatter structures. The universe, as far as our most powerful instruments can tell, appears to be overwhelmingly, almost exclusively, made of matter. This silence is not a failure. It's a crucial clue. It suggests that if anti-universes exist, they are either incredibly far away, beyond our observable horizon, or they are somehow fundamentally separated from our own, never interacting. The lack of cosmic annihilation events strongly weighs against the idea of matter and antimatter galaxies casually coexisting and colliding. This pushes us back to the early universe, to the first fraction of a second, when the asymmetry was forged. The answer, then, must lie in the subtle, fleeting processes that happened before matter and antimatter had a chance to annihilate on a grand scale. It points towards those powerful phase transitions, or the decay of exotic, long-extinct particles like those super-heavy neutrinos. The universe in its infancy was a volatile laboratory, and whatever happened there determined everything that followed. The stakes are immense. Unlocking the secret of the Baryon asymmetry isn't just about satisfying scientific curiosity. It's about completing the cosmic birth story. It's about understanding why stars burn, why planets form, why life exists. It's about the very foundation of our improbable reality. The struggle continues, pushing the boundaries of human knowledge as we desperately seek the truth about why the universe chose to build Urs instead of vanishing into pure light. The universe is still hiding its most profound secret, but we are relentless. We began this cosmic journey staring into the impossible void, asking why we exist at all. And what we've discovered is not a simple answer, but a profound, almost terrifying truth. Our universe is a survivor. It is the improbable winner of a cosmic war it should have lost. The very atoms that forge your hands, your thoughts, your consciousness, they are the triumphant remnants of a battle fought in the universe's first breath, a battle where matter barely, miraculously edged out its annihilating twin. This isn't just a scientific puzzle, it's the universe's deepest secret, etched into the fabric of reality itself. It forces us to confront the idea that the laws of physics, as we currently understand them, are incomplete. Something fundamental is missing from our cosmic instruction manual. Whether it was the fleeting, asymmetric decay of titanic, long-vanished neutrinos, or a cataclysmic, universe-shattering phase transition that ripped reality open, or even the existence of an unreachable anti-cosmos, the answer to our existence lies hidden in the universe's most violent, primordial moments. Our presence, this vibrant, complex cosmos, is a testament to a cosmic cheat. It is a glorious, improbable defiance of perfect symmetry, and the hunt for that defiance continues, pushing the boundaries of human ingenuity, from particle accelerators that momentarily recreate the Big Bang, to telescopes that scan for the ghostly signatures of antimatter annihilation across billions of light years. The struggle to understand this asymmetry is a struggle to understand our own cosmic birthright, the bizarre, beautiful accident that allowed us to be. We are not just observers of this universe. We are its living, breathing paradox. Every star, every galaxy, every heartbeat is a monumental question mark against the backdrop of a cosmos that, by all rights, should be empty. And perhaps that is the most awe-inspiring truth of all, that from a fundamental imbalance, from a cosmic whisper of preference, surged forth the entirety of creation. Our existence is not just a statistical anomaly, it is the universe's most profound, enduring mystery, daring us to unravel its improbable genesis. Tell me what you liked or disliked about this video. What do you think could be changed to make it better? I read every comment and will respond to every suggestion.